All right, good morning. Today we are looking at applications of thermodynamics. The notes are going to look just a little bit different. Instead of following the curriculum I picked out the um, parts of the unit from the book, and we're just going to follow the book. So maybe hopefully it'll be easier to use. I would appreciate your feedback. All right, so here we go. Applications of thermodynamics. This is our last unit. This is unit 9. So let's start by talking about a spontaneous process. A spontaneous process is something that happens with outside help. Without outside help. So it just happens, like the rotting of a banana just happens, right? A banana is going to rot. We can slow it down, yes, but eventually it will end up rotting, right? Or my coffee cooling off here. Awesome. A non spontaneous process, then, is something that requires a little outside help. And so, kind of one that we could think of there is like the gasoline in your car. It doesn't just start burning up, it needs a spark to get that to happen. Now, one thing that we need to talk about here is we are talking about spontaneity, if it happens or not how slowly it happens. Like the rotting of a banana, most of the time takes a time, right? So we're not talking about reaction speed, we're talking about spontaneity. Does it go on its own, even if it is going very slowly? All right. A lot of times, the non spontaneous processes can be made spontaneous with the addition of, most of the time, we're talking some form of energy. Like in the case of gasoline, we need a spark to get it to go in. And so the spark would be a piece of energy, right? So sometimes it needs like a little piece of energy to kind of get it going. So now let's jump into what is called entropy. All right. Entropy, and the second law of thermodynamics. Let's kind of look at some background information. So when ice melts, what do we have happening to the ice melting, right? Heat is added, right? Enthalpy, remember, is talking about the heat or energy added. So enthalpy, we're talking about heat has to be added, right, for ice to melt. So if we look at our energy diagram, that we start at a lower energy and then it goes up, something like that, right? It could be lower, it could be higher, but our products are at a higher energy than our reactants. Now, looking at the energy diagram, it kind of doesn't seem like it would be spontaneous because up here we said we needed to add some form of energy. But we do know that ice will melt at room temperature, right? So based on the energy diagram, no, it doesn't look spontaneous. Whoa. But obviously it is, right? And that's because we had to add energy, right? And we talked about adding energy up above. So there must be something else at play here. So what is happening on the molecular level? When ice melts, what do we have? Let's kind of look at some particulate diagrams. So here's my particulate diagram. And so we've got ice, the solid, right there, right? And then when we melt it, our ice turns into a liquid. All right, so what's happening on the molecular level? The particles are getting more spread out. All right, so let's look at like the dissolution of sodium chloride in water. What happens there? So we've got a solid piece of sodium chloride, boop, 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 and here's some water around it. And then when we dissolve it, still got water, but now those pieces are kind of spread out. All right, it's one too many pieces, so let's take one of those out. All right. So that's what we're introducing ourselves to. There's got to be something else at play than just like the energy change, because according to this up here, it doesn't look like it would be spontaneous. And what else is at play is what is called entropy. Entropy is a huge physics topic, but we're going to talk about it in chemistry. And entropy is the amount of disorder. All right. So if you look at my room at the beginning of the year versus the end of the year, that front desk is usually fairly organized, but towards the end of the year, it gets kind of crazy and there's a lot of stuff going on with it. All right. So we're talking about disorder, and up there, that is what is happening. Our ice was becoming more disordered, our sodium chloride was becoming more disordered in the water. All right, so let's look at our formula. S, still entropy. All right, and this is actually how we calculate entropy. K is a constant, all right, and this is, we take Boltzmann constant and divide by Avogadro's number. Now, are you going to have to do these calculations on the test? Probably not, but it's good to know that Boltzmann constant over Avogadro's number. So this is really still a constant, right? We're talking about a constant. Our focus here is on W. W is what we call microstates. And we're going to talk about those more down below, but the more microstates we have, the greater the entropy. So if W increases, entropy increases. And that is what is going into play up here, right? We have our entropy increasing because we have more microstates. Now let's talk a little bit more about microstates. All right, and microstate is a good way to look at this is like it's a snapshot on the molecular level. So if we could, we would just take pictures of each particle and it's each individual shot, right? So let's look back up to like our ice, right? There's not a lot of microshots or microstates here with the ice being solid, right? There is not a lot of movement of those particles. But as they spread out, we get more and more microstates. And as they're in the liquid, they are just continually moving. And so we have a ton of microstates. So that's where we have our entropy increasing. Macrostates is kind of looking at it at the whole picture, looking at the big picture, all right, as a whole, right? Thinking of it as a whole instead of the molecular level. All right. We kind of talked about how to visualize microstates. If we could just take a little camera each time a particle moved, a particle, we're talking about a particle. So think about the millions and millions of microstates that we could have. All right. So microstates, we're taking a photo of each time the particle or particles move. So that's kind of an aggressive amount of microstates, which is why you'll never have to calculate that because who can actually count how many microstates we have? All right, that brings us to our second law of thermodynamics. Our second law of thermodynamics says for any spontaneous process, let's get there, for any spontaneous process, the entropy of the universe increases. All right. So that's how we get spontaneous processes. The entropy of the universe is increasing. So that gets kind of crazy if you think about it, but there are a lot of ways that the entropy can change or we can have movement there. All right, let's continue on. Let's talk about this kind of the last thing. What if we have a greater temperature? What about temperature change? What do you think will happen with microstates? You are correct. As the temp increases, our microstates increase, which makes sense because they're going to be moving more. And we're talking about each time they move. Okay? And again, let's take it back to entropy a state function. If you remember a state function, that means it doesn't matter how we got there, just that we got there. Remember, I think we talked about climbing a mountain, right? Somebody could walk straight up the mountain, but they still made it to the top. Or somebody could take a winding path up the mountain and they still made it to the top. All right. So it kind of doesn't matter. Another one, you could, if you're competing in a marathon, as long as you're not worried about the finish and your goal is to just finish that 26.2 miles, as long as you finish, it doesn't matter if you ran, walked, crawled, whatever, you got there. All right, so a lot of times what we do to calculate this is delta S. Remember, that's change in S, so we take S final minus an S initial. All right, see you on the next video.